First, I want to thank the organizers for inviting me to give this talk. So I'm going to talk about Manin's conjecture for Châtelet surfaces. So first, what is a Châtelet surface? So let delta be a rational number such that negative delta is not a square, and let f of z be a square-free polynomial of degree 3 or 4. Then a Châtelet surface will be a proper smooth model of the affine equation x squared plus delta y squared is equal to f of z. So some historical background on Châtelet surfaces. Well, Châtelet originally studied the surface x squared minus ay squared is equal to z minus e1 times z minus e2 times z minus e3. So this is the case when f of z is a cubic that splits into three distinct linear factors. This will be a cubic surface, and Châtelet showed that there's a finite parameterization of the rational points over a number field on this surface. Then later, in 1966 and 1977, Manin and Ishakovich established a birational classification of rational surfaces. And in this classification, these Châtelet surfaces, as defined in the previous slide, they appear as some of the simplest arithmetically non-trivial surfaces. And so one of the reasons why we care about Châtelet surfaces is they often serve as test cases for studying problems like the existence of rational points, the Hasse principle, weak approximation. They're also examples of surfaces that are not torque varieties or homogeneous spaces. So speaking of the Hasse principle, Châtelet surfaces can actually fail the Hasse principle. So if we look at the surface x squared plus y squared is equal to 3z squared minus 1 times 1 minus 2z squared, then Ishakovich showed that this surface will have solutions over the real numbers and p-adic numbers for every prime p, but it has no rational points. In other words, it fails the Hasse principle. And so what's causing it to have no rational points? Well, we're trying to set a binary quadratic form to be equal to the product of two quadratic polynomials. So what's going on behind the scenes is you need some quadratic reciprocity relations to hold in order for there to be rational points, and these relationships fail in this case. More generally, this is known as a Brouwer-Manin obstruction, which is generally a cohomological obstruction to rational points. So if you think about the set of rational points on a variety X, they'll embed into the set of adelic points, but also they'll embed into the set of adelic points fixed by the Brouwer group of X. And if this set is empty, then it's known as a Brouwer-Manin obstruction. In the case of Châtelet surfaces, it turns out that a Brouwer-Manin obstruction will only occur when our polynomial f of z decomposes as the product of two quadratic polynomials. It doesn't have to occur, but it can occur in this case. And in this case, the Brouwer-Manin obstruction, it's easier to compute, and actually it always boils down to some sort of problem with quadratic reciprocity. So in 1987, Châtelet, Sansuk, and Swinnerton-Dyer studied the Hasse principle for Châtelet surfaces. And so in their seminal result, they showed that a Châtelet surface has no rational points if and only if there's either a local or Brouwer-Manin obstruction. So today I want to talk about Manin's conjecture. And so first we'll talk about the more general Manin's conjecture. So let's say X is a Fano variety over a number field, and H is an anti-canonical height on X. Then Manin's conjecture is about studying the number of points on X of height at most B as B goes to infinity. And it predicts that this count is asymptotic to some constant times B to the A times log B to the B minus 1, where this little a and little b are intrinsic geometric constants. And later, this leading constant was given a prediction by Pear. But I'm not going to focus very much on the leading constant in this talk. So what does Manin's conjecture predict for Châtelet surfaces over the rational numbers? Well, first, let's assume that our surface has a point. Then it predicts that as b goes to infinity, the number of points of height at most b grows like some constant times b log b to the rho minus 1, where this rho is the Picard rank of your Châtelet surface. And this Picard rank can be computed very explicitly So let's say that f of z decomposes as f1 through fr. These are going to be irreducible polynomials. Then the Picard rank is equal to 2 plus the number of irreducible polynomials, I, such that the square root of negative delta is contained in the field extension defined by fi. So something I want to mention about this statement is that here I've assumed that our Châtelet surface has a rational point. This assumption isn't really standardized across the various statements of Manin's conjecture. Sometimes you might assume instead that your surface or variety has a Zariski dense set of rational points or an infinite set of rational points. In the case of Châtelet surfaces, due to a geometric property called unirationality, if you have a rational point, then you already know that you have a Zariski dense set of rational points. So all of these assumptions will be equivalent in this case. Okay, so the next thing I want to talk about is what is this height? Because I said we were counting the rational points of height at most b. Well, we actually have a very explicit description for what this count will be. So it's going to be the number of tuples x, y, u, v, t, such that x squared plus delta y squared is equal to t squared times f of u, v, where this big F is the homogenization of the little f. We have some GCD conditions. So we want the GCD of x, y, and t and the GCD of u and v to be equal to 1. And then we have the height condition. So we want the size of tu squared, tv squared, x and y to be at most b. And this is coming from the pullback of the natural height on projective space via this morphism from the Châtelet surface to P4. And I didn't write down explicitly what this morphism is, but I just wanted to say that this morphism gives an isomorphism from the Châtelet surface onto its image, and its image will be a del Pezzo surface of degree 4 and has this explicit description. Okay, so the result that I want to talk about today is that Manin's conjecture is true for all Châtelet surfaces over the rational numbers. So specifically, what are we going to prove? So we're going to modify our height a little bit. So instead of looking at x and y being at most b, we're going to say that the norm of x plus minus y times square root of negative delta is at most b. These heights are equivalent up to some scaling, but this just turns out to work better with the method. Then we'll show that as b goes to infinity, the number of points of height at most b is some constant times b log b to the Picard rank minus 1, plus an error term of b log b to the Picard rank minus 1 minus 10 to negative 10. Moreover, we're not going to assume a priori that we have rational points. This asymptotic, it will always hold, but the leading constant will be 0 if and only if there's a local or Bauer-Manin obstruction, and then by the result of Châtelet, Lenz, and Suk and Sunich and Dyer, that means that you didn't have any rational points to start with. So I want to make a few comments about this statement. So first off, this error term here with the savings of log b to negative 10 to negative 10, it's not optimized, but I think that there's a limit to the method where the limit's somewhere around log b to say negative 1 over 1,000. So it's still a small power of log b. It just maybe doesn't have to be this small a power of log b. The second and more substantial thing I want to mention is a little bit more about the statement that the leading constant is 0 if and only if there's a local or Bauer-Manin obstruction. So in the method of Châtelet, Lenz, and Suk and Sunich and Dyer, where they showed that there's a local or that there are no rational points if and only if there's a local or Bauer-Manin obstruction, they derive some sort of algebraic condition for when there is a local or Bauer-Manin obstruction. This connects to their fibration method and uses these auxiliary varieties. And so we actually show that this constant is 0 if and only if this algebraic condition holds. However, when f of z is an irreducible polynomial, you have to do a different set of fibers in their method. But when f of z is irreducible on the counting side, it's actually when the constant is easiest to look at. And in this case, the leading constant will be a product over primes of some local densities. And you can actually explicitly see that the Hasse principle will hold in this case, and the leading constant will be 0 if and only if something goes wrong at one of the primes or at the real place. Okay, so before I talk about the proof, I want to say a little bit about the history of this problem. So Manin's conjecture was previously known for all Châtelet surfaces when delta was equal to 1. So this is the case when you're looking at the sum of two squares is equal to f of z. And this was done by a collection of works of different combinations of the following authors. So Delabartèche, Browning, Desarnos, Pear, and Tenenbaum. I want to highlight two of the results. So the first one being when f is the product of three distinct linear factors. This is the case that Châtelet originally studied. And this was done by Delabartèche, Browning, and Pear in 2012. And it was a really important result because it was the first instance of Manin's conjecture for Châtelet surfaces for any Châtelet surface. And also introduced the use of the torsion method to count rational points and get asymptotics. The other result that I want to highlight is when f is either an irreducible quartic or the product of two irreducible quadratics, which was done by Delabartèche and Tenenbaum, and they had to introduce the use of Hooly's delta function to handle this case. It's also an interesting case because when f is the product of two quadratics, that's the only case when the Brouwer-Manin obstruction can show up. Something to note is all of these techniques that handled when delta was equal to 1 actually work as long as delta is equal to one of these numbers. And you might recognize this list of numbers as the set of delta that generate imaginary quadratic fields with class number 1. And I'll explain a little bit later about why the class number is important here. The last result I want to mention is that upper bounds of the correct order of magnitude were known for all positive delta by Browning in 2010. Okay, so just to give an outline of the rest of this talk, first I want to get our foot in the door with the case when delta is equal to 1 and f is an irreducible cubic, just to get started with the method. And then I'll talk about the use of the Hooly delta function to handle when f is an irreducible quartic. And then I'll talk about some new work. So that's when delta is any positive number, so you're allowed to have any class number. And this will overcome the class number issue. And then finally, I'll touch on when delta is a negative number. This brings on extra complications because now you're looking at an indefinite quadratic form instead of a positive definite quadratic form on the left-hand side. But before I start talking about the proof and the methods, are there any questions? Okay. Then we'll start with when delta is equal to 1 and f is an irreducible cubic. In this case, we can rewrite our expression for the number of points of height at most b as 1/2 times the sum of t up to b and the sum of u and v up to b over t to the 1/2. This is coming from the fact that we wanted tu squared, tv squared to be at most b. And then the number of ways of writing t squared f of uv as the sum of two squares. Something I've left out here is the GCD conditions. They don't come into play really in this argument. So for simplicity, I've left them out. Okay, so now let's look a little bit closer at our representation function, the number of ways of writing n as the sum of two squares. Well, we have a very clean expression for it as 4 times the sum over divisors of n of chi of d, where chi is a quadratic character mod 4. And so it has this nice Dirichlet convolution structure, and that's really going to be the starting point for the proof technique here. So first, we want to count the number of points of height at most b, and it'll turn out it suffices to get asymptotics on this inner sum and then do the sum over t at the very end. So think of x as b over t to the 1/2. What we want to understand is the sum over u and v up to x of r of f of uv. And so the first thing we're going to do is we're just going to plug in that nice expression for r of n, and so we get the sum over divisors of f of uv of chi of d. Next, we'll do a very classical trick where we just split up the sum over divisors of f of uv by when they're less than the square root of f of uv and greater than the square root of f of uv. And when they're less than the square root, we'll just leave it be. And when it's greater than the square root, then we'll know that chi of d is equal to chi of f of uv over d prime, for some d prime less than square root of f of uv. And then if we know certain things about the congruence class that u and v sits in, then we'll know that this is chi of f of uv times chi of d prime. And so our sum over d becomes a sum over d prime, which is less than the square root of chi of d prime. And so this reduces us to understanding, instead of this sum, the sum over divisors d up to x to the 3/2 of chi of d, and then now the number of u and v up to x, such that d divides f of uv. And where did this 3/2 come from? Well, it came from the fact that f was a cubic and u and v are of size at most x. So that means that f of uv is of size at most x cubed. And then we split up our divisors by when they were the square root of f of uv. So that's where the 3/2 is coming from. So in order to understand this expression, what we're going to do is we're going to try to count on average what this number of u and v up to x, such that d divides f of uv. And so this is a result of Graves from 1970, that if you look at the sum over d up to x to the 3/2, and then the difference between this count of u and v, such that d divides f of uv, and what you expect it to be, which is the number of solutions mod d to the equation times x squared over d squared, then you get a power saving upper bound. So it's O of x to the 9/5. So bounds of this form are known as level of distribution bounds, or maybe type 1 estimates. And this particular level of distribution bound can be proved either through Graves' original method, which was through Poisson summation, or you can also achieve it using some lattice estimate calculations. And so why is this good for us? Well, it allows us to substitute this expression for this count in our original expression. So in particular, we can now write this sum as x squared times the sum over d up to x to the 3/2 of chi of d, rho of d over d squared, where rho of d was the number of solutions to this equation mod d, plus an error term of x to the 9/5. But if we look at our main term, it'll be of size at least x squared, so an error term of x to the 9/5 is okay. So now we just want to know what's going on in our main term. Well, okay, in order to understand this sum, we're going to instead look at a Dirichlet series, which is C of S, which is going to be the sum over d of chi of d, rho of d over d to the 1 plus s. And this will converge for real part of s at least 1. And since rho is going to be the number of solutions mod d to this equation, it's going to be a multiplicative function. This Dirichlet series will have a nice Euler product expansion. And after you analyze the Euler products, you can see that up to a factor that converges for real part of s, at least say 3/4, this will look like the product over prime ideals in this extension defined by f of z of 1 plus the chi of the norm of the prime ideal over the norm to the s. In other words, it looks like the quadratic twist by chi of the Dedekind zeta function given by this field extension. And in order to understand this sum here, what we want to know is what's the behavior of our Dirichlet series at s equals 1, and we can see that its behavior, at least analytically, will match up to the behavior at s equals 1 of this L function. And we know what that behavior is. It's going to be either a pole if the square root of negative delta is contained in the field extension, or it'll be 0 otherwise. In other words, this L function has a pole of order of the Picard rank -2. So that's the connection to the Picard rank in the conjecture. And so putting this together, this means that this expression will be some constant that is either the value or the residue at s equals 1 of our Dirichlet series times x squared times log x to the Picard rank plus an error term that is good enough for us. And so now if we go back to our original question, which was counting the number of points of height at most b, we can plug in this asymptotic and we get the sum over t up to b of this constant times b over t. Just to recall, x was equal to b over t to the 1/2, so x squared is b over t, times log of b over t to the Picard rank minus 2. And now we gain an extra power of log from the fact that we have a sum over t up to b of 1 over t. And so now we have this constant times b log b to the Picard rank minus 1 plus an error term of b log b to the rho minus 2. Now, just to say a little bit about this constant, well, we saw that it was either the value or the residue at s equals 1 of this Dirichlet series. In other words, it's going to look like a product over primes of some factors. And you can show that these p-adic factors will actually be 0 if and only if there was something going on at the place over p, the p place of your original Châtelet surface. And so this kind of recovers the Hasse principle in the case when f of z is an irreducible cubic. Okay. Are there any questions about that starting case? Okay, so the next case that I want to talk about is when delta equals 1 and f is an irreducible quartic. And in this case, we're going to start the same way. So we have the number of points of height at most b, and we can write it as the sum over t, the sum over u and v of the number of ways of writing t squared f of uv as the sum of two squares. Again, I've left out the GCD conditions. They don't come into play in this argument. And so again, we have the number of ways of writing the sum of n as the sum of two squares, has this nice Dirichlet convolution structure. And after doing the same computation, we see that what we want to estimate is the sum over d up to x squared of chi of d, and now the count of the number of u and v up to x, such that d divides f of uv. And now our exponent is 2 because f is a quartic, and so u and v go up to x, so f of uv goes up to x to the fourth, and the square root of that is x squared. And now if we wanted to proceed in the same way as when f was a cubic, what we would want is some sort of result like this, where we have the sum of d up to x squared of the difference between our count and what we think it should be to be little o of x squared. Now, unfortunately, I don't know how to prove such a strong level distribution bound, but we do actually know something which is basically just as good. So this proposition the original proof technique came from Daniel in 1999, who got d up to x squared times log x to the negative 1 plus a little bit. And then it was refined very carefully by de la Bretèche and Tenenbaum using some extremely careful lattice estimates to get the following result. So if delta is any positive number, then if you look at the sum over d up to x squared times log x to the negative delta of the difference between our count and what we think it should be, which is this local count times x squared over d squared, then you will indeed get a little o of x squared here. And in fact, this is quantitative. It's x squared times some negative power of log x, where that negative power depends on delta. And so this means that at least we can kind of proceed as we did before. So at least for d up to x squared log x to the negative delta, we can substitute our count with what we think it should be, which is rho of d over d squared, up to a suitable error term. And so for the d up to x squared times log x to the negative delta, we get the contribution. The contribution looks like some constant, which is either the value or residue at s equals 1 of a Dirichlet series, times x squared times log x to the Picard rank minus 2, plus a suitable error term. However, that wasn't what we were originally trying to estimate. We actually wanted the sum of d all the way up to x squared of chi of d, the sum over u and v up to x, such that d divides f of uv. So we need to handle these larger moduli, the d that are in between x squared and x squared times log x to the negative delta. And so this is where de la Bretèche and Tenenbaum bring in the Hooley delta function. So let's define for a non-trivial character chi, delta of n chi to be the supremum over d and exponents v of the divisors of n sitting inside of some dyadic range of chi of d. And so we'll call this the twisted Hooley delta function because it's twisted by the character chi. And so you can show that the contribution from these large moduli will be bounded by the sum over u and v up to x, such that there exists a large divisor of f of uv of delta f of uv chi times this log x factor, and that's just coming from the fact that we had log x dyadic intervals in this range. And so why is this good for us? Well, first, I'm going to give an intuitive reason for why it's good for us, which is that this twisted Hooley delta function on average is less than any power of log x. On the other hand, if you count the number of u and v up to x such that there exists a large divisor of f of uv, you get something a little bit smaller than the trivial bound. In fact, you save a small power of log x. So it's bounded by x squared times log x to say to negative 1 over 400. But because delta n of chi is smaller than any power of log x, this will still be the dominant savings. Like it won't cancel out the savings that you get here. So more specifically, what's happening? So we're going to apply the Cauchy-Schwarz inequality, and we can see on the right-hand side, this sum is bounded by x times log x to the negative 1 over 800. On the other hand, on this side over here, we're looking at the sum of u and v up to x of delta of f of u v chi, but now there's a square because we applied the Cauchy-Schwarz inequality. And De La Bretèche and Tenenbaum showed that this sum, even when you're going along the polynomial values, will be bounded by x squared times log x to the rho minus 2 times a factor that's smaller than log x to the epsilon for all epsilon greater than 0. So as a result, the contribution from the large moduli will actually be an error term because we have this small power of log savings over the trivial bound. Okay, so why was it important to use the twisted Hooley delta function here? Well, as compared to some other functions that track your divisors. So first off, if you looked at, say, the divisor function, that on average will look like log x, but before we were saving something like log x to negative 1 over 800. So if we use the divisor function, it will completely cancel out the savings that we got before. On the other hand, maybe you look at the regular Hooley delta function, which tracks the number of divisors in a certain dyadic region. And this, at least on average, is smaller than any power of any power of log x. But we applied the Cauchy-Schwarz inequality before, so we actually cared about delta of n squared, and this on average grows small, like this on average is bounded by x times log x to the 1 plus epsilon. So again, there's a power of log x that will cancel out the savings that you had before. So this is why it's very important to use the twisted Hooley delta function, where you're twisted by a non-trivial character chi, because both it and its square are going to be bounded by any power of log x to the epsilon. So you'll still be able to retain your savings from the count of u and v, such that there exists a large divisor of f of uv. So let's just summarize what happened in the case when f was an irreducible quartic. First, when d was less than x squared times log x to the negative delta, we had a level of distribution result that allowed us to write this as some constant times x squared times log x to the rho minus 2. So this will be the main term plus a sufficient error term. And then using the twisted Hooley delta function, we bounded the contribution from these large moduli by x squared times log x to the rho minus 2 minus 1 over 1,000. So a small power of log. And so plugging this in, this means you get an asymptotic on this inner sum, and then the count of points of height at most b will grow like some constant times b log b to the rho minus 1 plus an error term that's b log b times rho minus 1 minus 1 over 1,000. So again, a small power of log saving, but it's still a savings. Okay. Are there any questions about that part? Okay, so now I'm going to talk about some new stuff, which is when delta is any positive number. And so let's start again at the count. So we want to count the number of points of height at most b. And so we again look at the sum over t and the sum over u and v. And now we're looking at the number of ways of writing t squared f of uv as x squared plus delta y squared. So again, I've left out these GCD conditions, but they are returning very soon. But we have bigger problems to worry about at the moment, because this representation number of the number of ways of writing n as x squared plus delta y squared, it no longer necessarily has the form of the sum over divisors of n of chi of d. And that was really the starting point for the previous argument. So now we need to find some new structure to use in order to start working with this sum. And that structure is going to come from the theory of modular forms. So again, just remember that delta is a positive number here. So consider the theta function, which is defined to be the sum over n of r of n e to 2 pi I n z. This will be a holomorphic modular form of weight 1 for gamma naught of 4 delta chi, where chi is going to be the quadratic character mod 4 delta. And since it's a modular form, we can decompose it into its Eisenstein and cuspidal parts. And correspondingly, this allows us to decompose our representation number as the Fourier coefficient of the Eisenstein part plus the Fourier coefficient of the cuspidal part. And now if you work with modular forms a bit, you might look at this and go, hurrah, okay, we're all good, because we know that the Ramanujan-Peterson conjecture holds in this case, and that means we have great upper bounds on the size of these Fourier coefficients of cusp forms. That's kind of true in this case. So the Ramanujan-Peterson conjecture does hold, and so it states that if C of z is a weight k cusp form, then the size of this Fourier coefficients of the cuspidal part will be bounded by n to the k minus 1 over 2 plus epsilon. And if k is at least 2, this does mean that these Fourier coefficient, the cusp form coefficients are much smaller in magnitude than the Eisenstein coefficients. But our cusp form is a weight 1 cusp form. And so that means that the size of the Eisenstein coefficients and the size of the cusp form coefficients are actually of the same order of magnitude. And so we need to do something a little bit more subtle. Nevertheless, that's still the decomposition we're going to look at. We're going to decompose our count of points of height at most b into the Eisenstein and cuspidal parts. Again, I've left out the GCD conditions, but they are returning quite soon. And why is this good for us? Well, the Eisenstein part will actually be a very recognizable thing. It'll still have this Dirichlet convolution structure. So morally, at least, the Eisenstein coefficients will look like the sum over d up to d dividing n of chi of d, where chi is the quadratic character mod 4 delta. In actuality, the Eisenstein coefficients are slightly more complicated. You can show that they're going to correspond to like genus characters or class group characters of order 2. These are equivalent. But they will still be determined by congruence conditions and have this Dirichlet convolution structure. So just for simplicity, for this talk, we're going to think of these Eisenstein coefficients as this. What's going on here? Why do we have this nice structure for our Eisenstein coefficients, or why should we expect it? Well, when delta was equal to 1, our theta function, you can define a theta series, it will be purely Eisenstein. And so the cuspidal part will just be 0. And so that's why the Eisenstein coefficients kind of look like the expression that happened when delta was equal to 1. And in fact, when delta has class number 1, the theta function will always be purely Eisenstein, and so there'll be this nice Dirichlet convolution structure then too. Okay, so for the Eisenstein part, we're going to treat it exactly the same way we're going to treat it with the same techniques that handled the delta equals 1 case. And you can show that you get some constant times b log b to the rho minus 1 plus an error term of b log b to the rho minus 1 over 1,000. And this will become our main term of our count of points of height at most b. And so the new ingredient in this any positive delta case is being able to bound the cuspidal contribution. And so now the GCD conditions are coming back because that wasn't exactly what the cuspidal contribution was. So recall that we wanted the GCD of x, y, and t to be 1. And after the appropriate Mobius inversion, we get this extra sum over divisors of t of mu of d. And then instead of a t squared f of uv, we have a t over d squared f of uv. And so this will denote as S of xb, and it's the cuspidal contribution. And so what we want to show is that this is less than b log b to the rho minus 1 minus some positive delta, because that means that it'll be less than the main term. And so how are we going to do that? Well, the first thing we're going to do is we're going to just change the order of summation. So we're going to pull the sum over u and v onto the outside, and then we'll do a sum over d of mu of d and a sum over t of lambda c of t squared f of uv. And then the next step we'll do is kind of illegal. We're going to pretend like these Fourier coefficients of cusp forms are completely multiplicative functions. They're multiplicative, they're not completely multiplicative, but at least morally that's what's going on in the argument. So we're going to make this assumption for simplicity at the moment. And that will allow us to just pull out the contribution from lambda c of f of uv to the outside sum, and say that our cusp form contribution is bounded by the sum over u and v up to b to the 1/2 of the size of lambda c of f of uv times the size of the sum over d of mu of d and the sum over t of lambda c of t squared. So why did we do this? We did this because this lambda c of t squared is a very recognizable function. It's going to be the Fourier coefficient of the symmetric square of your cusp form. In other words, if you create this Dirichlet series with the lambda c of t squared, you recover the symmetric square L function. And so that means we have very good knowledge of what this inner sum will look like. So if your symmetric square L function has a pole at s equals 1, then you know that it looks like the residue at s equals 1 of the symmetric square L function times x over d plus a power saving error term. On the other hand, if it's analytic at s equals 1, then you just get a power saving upper bound. So in the case when delta is positive, our cusp forms are actually always going to be in this first case, they'll be dihedral. But when delta is negative, they can be in either case. And it turns out it's, I don't know, I think it's simpler to present these all at once. So that's what we're going to do. So let's first talk about the case when we're not dihedral. And so our symmetric square L function is analytic at s equals 1. And so then our inner sum has a power saving upper bound. And so we're looking at the sum of d up to x of x over d to the 1 minus delta. And so this will be bounded by O of x. And so as a result, our cuspidal contribution will be bounded by b times the sum over u and v of the size of the Fourier coefficient at f of uv over the maximum of u squared and v squared. And then you can apply a sieve for non-negative multiplicative functions along polynomial values to show that this is less than b times log v to the Picard rank minus 2. And this is really good for us because the Eisenstein main term, the main term from the Eisenstein part, was of size b log b to the rho minus 1. So this is a full power of log saving over our main term. Okay, next what happens in the dihedral case? Well, now we'll just plug in our asymptotic for this inner sum, and we get that we have x times the residue at s equals 1 of our symmetric square L function, and times the sum over d up to x of mu of d over d. And then the power saving error term in the asymptotic will end up contributing an O of x. But the sum of over d up to x of mu of d over d, well, that just goes to 0 as x goes to infinity. So this whole thing is going to be bounded by O of x. And so plugging that in again, we can see that the cuspidal contribution will be bounded by b log b to the rho minus 2. And again, that's going to be a whole power of log less than our main term, which was of size b log b to the rho minus 1. And so we're okay. So what was going on behind the scenes of this estimate? Why did we get the same bound for when it was dihedral and non-dihedral? Well, what's going on is that since C of z is a cusp form, our symmetric square L function, it can have a pole, but that pole is of order at most 1. And since that pole is of order at most 1, that means that zeta of s inverse times the symmetric square L function, this function always has to be analytic at s equals 1. And so that's where we're deriving our savings from. Okay, just to summarize what happened in the delta positive case, we split our counting function into the Eisenstein and cuspidal parts. For the Eisenstein part, we treated it the same way as what happened when delta was equal to 1 to recover a main term plus an error term with a small power of log saving. And then for the cuspidal part, we connected it to the symmetric square L function and then got a full power of log saving over our main term. Okay, any questions about that? Okay, the final case I want to talk about is what happens when delta is negative. And this brings on some extra complications because now we can't just count the number of x and y, such that x squared plus delta y squared is equal to t squared f of uv, because there can be infinitely many x and y. This comes from the fact that a real quadratic field has an infinite unit group. And so we really need to use the fact that we had sharp cutoffs on what x and y were from our original height. So just to recall, we needed that the size of x plus minus y times square root of negative delta is at most b. And so now we have this expression here that isn't super obvious about if it has some connection to some sort of structure to use to really like get started with, like the way when delta equals 1, we had this Dirichlet convolution structure, and when delta was positive, we connected it to modular forms. This expression, I think, is not so obvious what to do with. And so instead of looking at this expression, we're going to study the seemingly harder sum when u and v are restricted to a short box in order to create a similar looking expression that we actually can deal with. So let script b be a box of length log b to the negative 10 to the negative 9. And let's define the argument of an element in your real quadratic field as the size of your element over the size of its conjugate mod epsilon squared, where epsilon is the fundamental solution to Pell's equation. In other words, any unit in your real quadratic field will be of the form epsilon to the k for some k that's an integer. And let's let I be an interval of length log b to the negative 10 to the negative 9. Then instead of counting nx of b, we're going to look at we're going to look at nx of script bi. So this is the same sum, but now we're going to take u and v to be in some scaling of our semi-short box. I say it's semi-short because it's technically a short box, but our length is like very slowly going to 0, so it's kind of a semi-short box. And then we're going to also restrict our argument of x plus y times square root of negative delta to be in this kind of short interval. And so our goal is to get an asymptotic on this expression that's good enough that we can just sum over all the possible short boxes and all the possible intervals to recover an asymptotic on nx of b. And so why did we do this? Well, restricting to x and y in a certain interval and u and v in that semi-short box allows us to count the number of units involved in this expression. So using Grossen characters and some somewhat messy computation, you can show that this expression is equal to some constant that depends on the box and your interval, plus an error term of log b to negative 10 to negative 10, times the number of ideals in our real quadratic field that are principal and have norm t squared f of uv, and the GCD of x, y, and t is equal to 1. And this expression is good because it looks a lot like the expression that came up when delta was positive. So in particular, what we're going to want to understand is the sum over t and u and v in the semi-short box of the number of ideals that are principal and of norm t squared f of uv. Now, if we go back to what we were doing when delta was positive, we were looking at this representation number, the number of ways of writing n as x squared plus delta y squared. But what was this representation number really? Well, it was the number of units in our imaginary quadratic field times the number of ideals in our imaginary quadratic field that were principal and of norm n. And then using the theory of holomorphic modular forms, we decomposed it into an Eisenstein and cuspidal part and then proceeded to analyze both parts separately. So in this case, we're counting the number of ideals in a real quadratic field that are principal and of norm n. And we can again decompose it into an Eisenstein and cuspidal part that come from a Hecke mass form now. And so for the Eisenstein part, we treat it like delta was equal to 1. And for the cuspidal part, we use the argument from before, and we can establish an asymptotic for this expression. There is a caveat, though, because we did restrict u and v to be in the semi-short box. And so we have to make sure that that restriction isn't going to come back to bite us in these techniques that were used for delta equals 1 and the cuspidal part. And so in the end, you can show that in both of these proof methods, restricting to a short box doesn't do too much, except for it gets you an extra factor of, say, L to the C. And our error terms were saving some log B to the negative 1 over 1,000 in the end. So this is why we're kind of choosing this L to be log B to negative 10 to negative 9, is just to make sure that this L to the C factor doesn't cancel out our savings from before. So we're just choosing this to be so small that L to the C is still smaller than log B to the 1 over 1,000. Okay. So that's how the main term is treated, or main term and some of the error terms are treated in the case when delta is negative, but a new error term is accumulated and it's hidden in this squiggly arrow with the computation with grossing characters. And the new error term looks like the sum over t and the sum over u and v in this semi-short box of now the absolute value of lambda c of t squared f of u v, where c is a cuspidal Hecke mass form, and it was formed using these grossing characters of infinite order. And now, if we think about it, putting absolute values around our cusp form coefficients just absolutely kills the argument that we were using before to handle the cusp form coefficients. So we need to do something else. And so now we'll connect this to a more general picture. So let's say pi is a cuspidal automorphic representation of GL2 of AQ. And let's assume it satisfies the Ramanujan-Peterson conjecture. Let's say KF is a splitting field of f of z. Then if the base change of pi to KF is a cuspidal representation of GL2 of AKF, then there exists a positive delta such that the sum over u and v of the size of these Fourier coefficients, even with the absolute values around them, is going to be less than x squared times log x to the negative delta. And so where is this coming from? Well, it's coming from knowledge about the Châtelet distribution of these Fourier coefficients of your cusp form. So I should mention that there's some previous results in this direction. So Elliott, Moreno, and Shahidi in 1984 looked at the case where f of uv is a linear polynomial. So it was actually a one variable linear polynomial, so it's just n. And then recently, Chiriac and Yang looked at the case of single variable polynomials. So they looked at sum of n up to x of lambda pi of f of n, where they assumed that the symmetric powers of pi were always cuspidal. Okay, so in our application, we have a cusp form that I said was a cuspidal Hecke mass form. And so you can separately show that it satisfies the Ramanujan-Peterson conjecture. And that's because this cusp form is really going to come from a combination of class group characters and this grossing character. And so all of these things are unitary. And so actually these Fourier coefficients are going to be bounded by like 2. Another thing to note is because we're looking at Châtelet surfaces, our f of z here is going to be of degree 3 or 4, which means that this extension will always be solvable. And so the base change is going to be a well-defined notion. And lastly, these cusp forms that appear in our application, they will always have a cuspidal base change. And that's because they're coming from these grossing characters of infinite order, and the infinite order means that their base change will end up being cuspidal. Okay, so the last thing I wanted to do was just kind of skim through some ingredients that went into the proof of this proposition. So some ingredients are first use a sieve on non-negative multiplicative functions along polynomial values, because we know that the absolute value of the Fourier coefficient of the cusp form, that is a non-negative multiplicative function. And this sieve comes from Nair, originally in 1992, but the version we'll use is by Delabertèche and Tenenbaum for binary forms. And so it shows you can bound it by x squared times the exponential of the sum over primes up to x of the size of lambda of p minus 1 times the local density, so the number of solutions mod p to this equation over p squared. And so what we want to do is we want to show that this expression here is negative delta pi of log x plus O of 1. And so you can relate this count of the number of solutions mod p of a polynomial f of u, the number of solutions mod p to this polynomial to the splitting field, and you can show that it suffices to understand the number of prime ideals in the splitting field of norm at most p of the size of lambda pi of the norm of p minus 1 over the norm. And now we're looking at this internal thing, which is the Fourier coefficient of pi at the norm of p, and we can relate that to the base change of pi to kf. So this will be the coefficient of pi kf at p. And so what we're trying to study is the sum of our prime ideals of our splitting field of norm at most x of the size of lambda pi of kf of p minus 1 over the norm of p. And now we're going to connect it to the moments of our cuspidal representation. So this is what I meant when I said it was related to the Châtelet distribution. So in particular, it's connected to the second and fourth moments. And so if your representation is non-dihedral, then it turns out the second and fourth moments will contribute negligibly. And if it is dihedral, then you already know that it's a Galois representation, and you can use some extra structure from the fact that it's a non-trivial Galois representation to separately get the bound that you want. Okay, so just to summarize what happened in this talk. So we wanted to show Manin's conjecture for Châtelet surfaces. And so in order to do that, we were studying these ways of representing n as x squared plus delta y squared, where we might need to add in this cutoff from the height function in the case when delta was negative, because then there would be infinitely many solutions to this. And so we decomposed it into an Eisenstein and cuspidal part. And then for the Eisenstein part, we analyzed it in the same way as when delta was equal to 1 using the Dirichlet convolution structure. And so this argument used the level of distribution bound. And then when f was an irreducible quartic, we had to add in this twisted Hooley delta function method. And for the cuspidal part, we connected it to the symmetric square L function and used the fact that this zeta of s times the symmetric square L function was always analytic at s equals 1 to derive some savings over the main term. And when delta was negative, we had an extra argument where we had these absolute values around our Fourier coefficients of cusp forms. And in this case, we needed to relate it to the base change of our cuspidal representation and get savings from the Châtelet distribution. Okay, so that's all I have. So thank you for listening. And are there any questions?